So our speakers tonight, we have Gordon Shotwell, Rima Al Shikh, and Fernando Pena-Silva. Please forgive me if I made a mistake there, or please correct me later. And we're going to start with Fernando first here in a minute, but I think I have another slide or two. And just want to shout out thanks to our sponsors who helped make this possible. We have Dash Hudson, Concrete Ventures, LaBarge Weinstein, ResMed, Lixar, Sandhill Financial, Red Space, Jonas Software Solutions, Inc., Tarka Labs, Proposify, and CodeCov. So thank you, sponsors, if any of you are here. Enjoy. We'll start with Fernando. If you'd like to come up, I'll load your slides.
Well, thank you to Halihax for inviting me, and also Wattpad for hosting. I'm going to make a disclaimer. I work for Nova Scotia Power, and as you can imagine, because of the hurricane, there was a lot of work going on. And I've been working on 12-hour shifts since Friday. Before Fiona hit us, they pre-staged us in different places just to get ready. And so if my brain looks a little bit slow, please understand. Well, anyways, I'm going to start. So I'm going to speak about some fancy stuff we're currently doing with all data and trying to combine the legacy data we have with the new data that's coming through with the smart meters. So I'm going to start the intro with a little bit about me. I'm a data nerd. I've done a little bit of math, physics. I worked also in healthcare in the past in doing epidemiology, and now I'm doing energy. Always, though, dealing with data and trying to find insights and do predictions, et cetera, et cetera. Currently, my role is being a load forecaster. I do forecasts on mid to long term. We have other forecasters who do it short term. In my case, I do it on a 1 year and up to 10 years basis. So the company can and the government can make decisions about where to go in terms of their capital expenditures, or also what are maybe things needs to phase out from the system. But also, I'm one of the data science Meetup hosts. So if you know me for a while, you know that I've been hosting these meetups. And thanks to Halihax, now we partnered together. So we're going to be bringing those starting next month. Well, we already had one event, but this is not the data science meetup event. Happily to be here, though. I'm a volunteer lead for data for Good Maritimes chapter, which is a volunteer-led group of data enthusiasts that help non-profits with their data analytics needs. You should have a look on that, because if you ever feel, I should have put a link, if you ever feel like you have a little bit of free time and ready to help some nonprofits, they always short staff, so it would be nice to do some data analysis for them. All right. So back in 2019, we started to upgrade all the around the 500,000 electric meters we have into smart meters. We call them AMIs, Advanced Metering Infrastructure, but out there in the public, they're known as smart meters. Currently, we have about 95% of customers that have been upgraded, but not all of them have been getting the benefits of the information. We have about 80% of bills that are being created through the AMI system, but we need to get there. And we're going to get there by the end of the year, at the worst, the beginning of the next year. We estimate that we will collect every year about 15 terabytes of data from smart meters, and that's going to get piled up every year. And we also have other system and other data tables that we can merge to that, but this is, let's call it, it's a dynamic table that is filled every day with the information that we collect from your premises, guys. Some of the benefits to have smart meters include daily remote reading, better insights. We're going to have websites in which you can go and see your daily consumption, so perhaps you can adjust your own consumption. And also we'll give you some estimate about, from that, kilowatt hour you spend during the day, what portions are being waste or used in terms of heating and other appliances. We're also going to improve our response times, because if a smart meter is sending data all the time, we can also see when they're shut down, especially when we have a storm, and we can sort of triangulate where those outages or broken meters are. And what I'm going to be talking about later today is new optional time of use tariffs. We're going to offer tariffs in which perhaps if you adjust your consumption, you'll get a benefit in your bill, and we're going to get a benefit that we're going to shave some of the peak demand out of the system. After that, after you collect the data at the meter, the data is sent to a meter data management system, MDM, where we store the data for 2 years. But that data gets replicated right away into a system in which we, the analysts, use, and also the billing system send you the final bills. But before we get there, the old meter data do not become useless right away. This legacy consumption information can be organized in a way that can be combined later on with the smart meter data, because the customer is still the same. We still have a number for you, your number 10, and we have all the legacy historical data from you, which if you were familiar with, you would get a bill every 2 months. So that's the frequency in which data was coming. Now with the smart meter, that frequency will change. It's much faster, but we still want to use that data in order to do some type of trend analysis per customer or per groups of customers. So as I said, the company has decades of customer data that can be leveraged for trend analysis and attach at the starting end of the new smart meter data. So I'm gonna talk to you about a little big project we did a couple of years ago, just to get in preparation for the smart meter data. So one of the, as in the bullet 2 says, when in the old system, when we used to send a bill to you, the meter reader, the person who go to your house, would come at different dates. Someone will go on the Monday first, another meter reader will come on the second day and third, and so and so. So you can imagine that when you have a table with the read, how many kilowatt hours you consume between the last month and the current month, with a date attached to it, and every single customer have more or less a different date. So what we're thinking is, with the smart meter now, it's going to be so easy to aggregate information and say, I want every customer information for the end of the month, the 30th or the first 31st of the month. It will be very easy. So how can we attach the old legacy data with the new data and try to make it more or less calendarized, we call it. So we create a little bit of automated code where we will feed, the table looks better there than here, but this is a table, and I make invisible all the account numbers and all that information you don't care. But you can see that you would get bill dates, and the other interesting quantity will be the usage. These are kilowatt hours. And as you see, there's so many different dates of consumption there. So how can we organize this data or estimate this data in a way that all the consumption dates are on the 31st, let's say, of the month? So just to make a toy example of this, if you would have almost 3 years here of data, 2 years of data, and it comes every 2 months, you can plot it on a sales versus time, and every 2 months you would have the consumption. This could be, for example, this could be one customer, and it would look this way. So the task what we wanted to do is, can we shift this, and every line here indicates the end of the month, so can I shift those points automatically for all the customers and shift it to at the beginning of the month? And also, we also wanted to, because they come every 2 months, we also wanted to interpolate and go to a monthly level. So can we turn these reads or this consumption every 2 months into a 1 month? So how can we do that? So the first things we did is we turned that previous figure into a cumulative sales figure. So it's basically the points that I showed you before, but now it's cumulative. So every month you get the aggregate from the previous one. That's why you see it always going up. This is the same customer I showed you before. It's just on aggregate level. This is going to result in a much easier way to follow and do math with it. Because if from that previous figure that I showed you, I calculate this difference, the difference between 2 consecutive points divided by the time, that's basically the rate that you're paying. Now, depending on this time period, it could be the daily rate, it could be the monthly rate, so and so and so. It depends on how granular is your data. So as if you want to remember something from your calculus days, when T2 approaches to T1 in this series, this quantity here looks like a derivative. So in code, in most of the code these days, you could use Python and R. If you use some type of interpolation routine, these are easily calculated. You just call, give me the interpolation, and the derivative of the interpolation is very easy to calculate, so it's automatically. So we try to find these functions, and then if you want to understand, to calculate the sales between a period, let's say T1 is the first day of the month, and T2 is the last day of the month, you calculate the integral of that, and that will give you an approximate value. So, from that figure that I showed you before, we first wanted to turn from every 2 months into a monthly series. So we end up having these little dots here. But just to check how far away these ones are from here, we can also add them every 2 points. We can add them just to get into the bi-monthly series. And I'm just plotting that figure here. The points are shift because that's what we wanted to do. We wanted to go from billing this customer on the 15th into the 31st. And here, I forgot to tell you, I'm doing a spline interpolation, which is a type of a cubic interpolation. And it does a pretty good job. So I did this for one customer, but once you find that algorithm for one customer, of course, you can replicate it and do it for the 500,000 extra customers. And what you end up is with a huge organized table for all customer premises, and it's very organized. Well, in this case, I put it on the 1st, but you can do it on the 31st. And it's very easy to handle. You can, if other teams in your company wants a smaller set of this data, you just can easily. In this case, we also label them by premise number, so we can give them a smaller table, and it's going to be easy, especially in the company. We also have people who work with Excel, so you have to give them something more simple to use. So if we give them something very well organized, it's easy for them to analyze and do whatever they want with it. So now we're going to have that legacy data very well organized, ready to attach in the starting point of the AMI data. So let's get back to smart meters. So one of the things I mentioned is that among the benefits of the AMI read is the ability to offer new optional rates for customers. So currently we have a pilot going on, and it aims to lower the bills of customers that are willing to change their consumption habits. Here we make a little survey at the beginning for these pilot customers. What were the most likely things to do during the start of the program? And this is what they told us. That they would change when they wash their clothes, so they will adapt the time at which they're washing the clothes. They also would run their dishwasher overnight. That's 68% of the customers who are enrolled in this program. And 65% of them would keep the lights turned off during peak hours, and so and so. We had 2 new rates, and I'm going to explain you what are the rates. One is called CPP, another TOU. I will explain what are those. These were the targets in terms of how many customers we wanted to enroll in this pilot. For CPP, we're about 500. For TOU, we're about 1,000. CPP wasn't that popular. You can't force people, so it is what it is. So we got about 60% of them on CPP, but a very good number, 76% in TOU. And I'm going to explain now what are those. So CPP, or critical peak pricing, basically when the company will send these customers an email or some type of communication that a peak event is coming. And peak event is basically all Nova Scotian during the winter time using their equipment, electronics at the same time. And that puts a lot of pressure on the system because we have to create that energy. And if we can sort of move people away from using their electronics or their appliances at that time, that will benefit the entire system. So currently we're charging 150 cents per kilowatt hour. When they send you this email at 4 p.m. the day before, it's only during the winter, and it's for about 4 hours. In all other hours in the winter period and all hours during the summer and in the spring, it stays off a flat rate of 13 cents per kilowatt hour. So it's a hefty jump. You go from 13 to 150, but the takeoff is basically that you have to adapt and try not to use your appliances when it's more expensive. So overall, you're supposed to get, if you change your habits, your consumption habits, you will get savings at the end of the day. The other one is, so the other details about this is the company cannot call more than 22 winter peak events, so no more than 22 emails during a year, and no more than 3 within a week. The other tariff is called time of use, and this one has, it costs about 32 cents per kilowatt hour on weekday peak hours, and 16 the rest. And these, you're not gonna get an email. You always need to be, we tell the customer what are the hours they shouldn't be, or they should be changing their habits, and these time periods are fixed. So it's basically they have to change their habits during the whole winter period. They're not gonna get any advice from us, a peak event is coming. No, you gotta adapt for the entire winter period. And that's the difference, is basically the double what it cost you before. So for some reason, this is getting more popular than this one. We also suspect there's a lot of people who didn't need to change their habit that much. When they saw this tariff, they probably say, hey, this is me, so I'm gonna get a benefit right away, right? So the question the analytics team, the load forecasting team was asked is, how do we measure the effectiveness of this program? So it all, and as I mentioned there, it's all about matching. So we early on decide that, and also with consultants, that per every customer in this pilot, it was going to be good to identify a similar customer that consumes energy at the same rate, but also has a similar demographics profile. Because you can imagine, even if you consume the same energy than two customers can look alike in terms of consumption, they may have a different house, they may have different insulation, different even heating equipment during the winter time. So you try to reduce the variance by pair them together. So once you find the match, then you could do a statistical analysis and can estimate the average savings per period. So how do we control for house and premise demographic differences? So as I mentioned, consumption of two customers may be affected differently by the level of the heating insulation the premise has, the location. You're right, these tariffs are available for all Nova Scotians, but someone who lives in Halihax has a different weather than someone who lives in Cape Breton. So, and your thermostats, or during the winter time especially, you turn it on and off depending on your local weather. And also, it changes with your heating appliance, etc. Now, Nova Scotia Power, for good reason, does not collect demographic information from you. We do run surveys customer surveys once in a while, and that will give us a sample idea. So how can we how can we make sure that we are pairing two customers that really look alike? So we came up with a clever algorithm in which we do a neighborhood criterion. So first of all, you start thinking, okay, I want to minimize the variance between the weather, so we need to look at people in the area. So you can look at postal codes, or you can look at coordinates, so and try to make that distance minimum. And we in the power company, we also know that even if two houses are very close by, they can be fed by a different line. And that can tell you a little bit about the history of that neighborhood. One neighborhood could have come up decades before the other one, even if they are next to each other. So we drew a line, and here I'm showing here, this is the map, how it looks in our system. And unfortunately, the resolution is not helping here. But here, this is Young Street, this is Almond Street, and the blue line here is a feeding line that is feeding all the customers around this area. And if you only do a criteria in which you try to find close neighbors, you may find yourself paired with a customer who is on the line versus someone who is not in the line. So the criteria uses two approaches. You need to match to be in the neighborhood in terms of distance, but also you need to be on the same feeder. So once you fix that, you can claim that you have reduced the variance between these two customers. And variance could be, again, the quality or the conditions of the houses. It could be income. So all of these are being reduced by this approach. We don't have the exact information, but through the surveys, you can compare your assumptions versus the surveys we have, and we've done a pretty decent job in that respect. So once we've done that location or neighborhood-based approach, the next thing we're going to do is match by consumption behavior. So we can compare this time series between these two nearby candidates with a metric called Euclidean distance, and it's done here. It's not that difficult to understand. It's basically the sum of the different squares. If you put in this graph, in a graph, time versus consumption, you put two customers together, you calculate those differences, you sum them up, and you come up with one number. So you can imagine I can do this for several candidates and find the minimum, and then I have the closer control that I can use for later comparison. So by having the two approaches, the neighborhood plus this Euclidean distance approach, I can find the right controls. So because we have about hundreds or up to thousands of customers, I didn't want to show you the individual customers. So what I did is aggregate, and I calculate averages. So in the left-hand side, I'm doing a comparison of the pilot averages of all the customers in the pilot versus the control, but this control is every customer in Nova Scotia. So there's no filtering by neighborhood, there's nothing like that. So you see a larger gap compared to this one that does use that approach that I'm showing you before. So now we have a way to estimate, and I forgot to tell you, I do these comparisons before the pilot start, because once the pilot start, of course your behavior have changed. So you're not apples to apples anymore. So you do these studies historically with the historical data with 1 or 2 years in the back before the pilot start. So then you decide who are your controls, and then you move further and you see the differences as time goes by. So here I'm showing you the savings basically in average. So I'm showing you two types of customer groups. We have the non-electric and electric. The difference is that we have customers who have heating using electric heating, and some other customers who don't have electric heating. So basically around the peak hours, you will have a jump. This is basically the difference between control and pilot. And you do see the jump at the peak hours. We usually have in wintertime either morning peak hours or evening peak hours, and they sometimes happens at 7 a.m., 8 a.m., or around 6 p.m. So those are the savings. Now we had to file recently, very recently, as last month, a progress report to the utility and review board, just to show how we're going. Now, this pilot runs for 2 years, and then we're going to decide if either we're going to stick it that way and offer it to everyone, or maybe we'll do some changes. So overall, when you aggregate all the customers, these are the quantities we're saving, which is about 12 to 10% in their usage in the evening and morning peaks. So, it's looking good. And next year is going to be the final year, so we'll be more confident with the results. Now, finishing it, as I said, we are in this big data domain in which another thing I forgot to say is that we're collecting data from customers every 15 minutes. Every 15 minutes, the meter that you have outside your house is storing data, and once a day, they've been read. So you get all those 15 minutes that you collected during the day. So suddenly, from going to 2 months, we will get your information every 2 months. Now we're getting your information every 15 minutes. So it became big all of a sudden. So our analytics are gonna get enhanced because of that, and we're gonna combine the old legacy consumption data with the MI data just to get new insights about our customers. And as I said, the control group matching, the Euclidean distance are statistical metrics to evaluate the pilot savings versus the regular customers. Thank you.
Hi, guys. So, thanks so much for the awesome talk. I got my power back an hour ago, so hey! I'm very honored to be giving my first technical talk in Nova Scotia. This was before in Dubai. I used to give to auditoriums of developers and stuff, and this is the first time I give a technical talk in Nova Scotia, and I'm really, really, really happy. So thank you for that. Speaking of being happy, my name is Rima, and I am the founder of Begin AI. And what we do essentially is personalization. And the reason why we're doing personalization is because I feel like every application has the need and the opportunity to deliver, let's call it digital happiness, because we can't, deliver the full spectrum happiness through AI, but let's say digital happiness. Today, when I was coming here, I opened Uber. It didn't ask me, you want to go by horse or where are you going, or it just said, hey, where are you going? I'll fix you up. And Uber Eats is even worse. It just says, hey, are you hungry? I'm like, how did you know? So, and then it tells you what food you might like to eat, right? So it's pretty cool, and it almost, tricks me every time. Like, yeah, I'm hungry, I want to click this, right? And, Netflix, Amazon, Facebook, all these guys, Netflix, 75% of their revenue comes from recommendation systems. That's a huge number, right? 75%. So they're a big company because they have a recommender system. And same thing with TikTok. TikTok is technically a recommender system. That's all TikTok is, right? They're like a huge recommender system. And Facebook got sued a whole bunch of times just because of how good the recommender system is. And Amazon's 35% of their revenue is recommender system. And if you guys game, the best gaming companies in the world have the best recommender systems. But it also feels like your girlfriend is cheating on you. It's like, because they kind of they're really nice to you, but because they steal your data, right? So it's like, so how do they do all this, right? So if you come to it, you're as a company that goes beyond seed stage, so you have 5 million users, and you're like, okay, cool. Now I have 5 million users. I have 5 million, a lot of books or something, or education, or whatever your company does, really. You're at a situation where you gotta optimize your experience to keep your users engaged, or you're gonna lose them. And I've experienced this personally with my first startup, and it was a freelance marketplace. Because when we were really small, it was really easy. We just said, put a job, you find a job, it was an easy match. But when we had a lot of jobs, a lot of freelancers, we had to get smarter about it. But it's so freaking hard to build recommender systems. They're so expensive. Privacy is a huge problem. But if you close your ears and you're like, I'm not going to listen to the crowd. I don't care. I'm not going to listen. And then you're like, I'm going to try to build this. The biggest challenge is actually the high velocity and high volumes of data. It's so hard to manage events that are coming at such frequency and make sense of them. Because think of it. You got to load like a massive data set of like what users liked, what users disliked, what did they click, what did they view. Did they go the whole restaurant menu? Did they just see one item and they swap back? All of these events are generated at a high velocity. And you're talking about like billions of events if you have 5 million users. And try to load billions of data points in your Jupyter notebook. Can you? No, your laptop will crash, right? You go to Databricks, and then your boss calls you and you're like, why am I paying hundreds of thousands of dollars for, did you do something in this project? No, we're still POCing. Holy shit, shut down that project, right? So you see where that cycle is going. And then let alone, the math and all that stuff. So I thought there was an opportunity there, and we tried to rethink the process. So what I want to show you today is like how we rethought the process of personalization and what we brought into the mix and how we tried to rebuild the recommendation system infrastructure. So step one, we said, can privacy be profitable? Funny thing is Google proved it can be, yet Google doesn't use it. So it's like, yeah, anyway. So Google invented this technique called federated learning. Turned out federated learning on its own is a promising idea, but it's not a good enough idea to build what we want to build. So we came up with a technique which is allows us to process data on the edge, on devices, and generate basic, simple embeddings of the data, and then send it to central storage for processing. And that turned out to be an extremely profitable solution. From a time management perspective and from a storage management perspective, because I'm not storing everything about the person, every event that happened, I'm just storing the meaning of these things. And once I've done that, we then looked at like possible ways to store this information, and we figured out like knowledge graphs are the best way to go about it. And then, we brought a bunch of techniques like what I just described is a form of differential privacy. So like when we process, we eliminate a lot of information about the user. Feel free in the Q&A to ask me about like the privacy techniques, but I'm not going to focus a lot on them. But essentially what we did is, like I said, as the user does a lot of interactions, we have an SDK, so we have an Android SDK, an iOS SDK, a Python SDK, JavaScript SDK, and you might ask why Python SDK if we're saying edge, but we can be blind to the fact that people have had stored a lot of information already, so we want to allow you to do distributed processing anyway. So you can process the data that you have in a server and the data that's on a device and whatever, and generate the embeddings from it. So our SDKs, given a description of the data, will generate the embedding and send it for learning. And then actually, I'm going to mention, since you're all data scientists, once the training is done, we can our SDKs also support inference on the edge. So you don't necessarily have to do high volume server requests to do inference, to say like, can you tell me what should be the next movie I show to the customer? You can ask that question on the edge without going to the server. And that saves latency. So basically, this is how our database looks like. Brilliant, eh? So, so this is a node, which is the blue dot right there is a person, and then the circles around them is the books they interact with. And I don't know if it's visible, but the edges of the interaction are a sentiment. So they say like, the blue interacted positively with that dot, interacted negatively with this dot, and it gives us a summary of the interaction. We don't actually really need to know what the interaction is. We just need to know the meaning of the interaction. And the highlighted dot there, this is what you see, and this is what we see for them. And what these are are embeddings essentially, and we see the first thing we get is the first generated embedding of the user. Actually, I have that in the demo. It might be better to switch to my laptop if that's okay in a second. So this is a book. What you can see is we have an ID, which might as well be the wind speed in Halifax. We don't really know what that ID means. And then you see like different versions of the embedding. So like the embedding row means the first version of embedding we received based on, it has like a number 34, which tells us based on what schema this was generated. And then you see stuff like embedding normalized. So this was normalized for a certain objective. And then if you look at, if I look at the person, you see like we have a lot of stuff about this person, but if you go to the row embedding, actually it's empty because this customer didn't tell us anything about the user. So we generated embeddings based on the position of this user in their context, in their universe. So they're like, based on one of the neural networks we train, it's called IOU. It's an IOU-based network, so intersection over union. So what it does is tries to generate an embedding for this person that positions them closer to the things they like and further away from the things they dislike. And that makes the embedding of this person really smart, and all we have to do is a cosine similarity to say, hey, show me all the books this person is gonna like, essentially. And in practice, so what I'm just gonna go down here so you can see. What we do is like, you go and you just like describe your data schema. So I'm just gonna take one like here. This data schema essentially is what the user has to tell us. So they give us like, so what they know about the book, they say like, we know their average rating, which is a number between 0 and 10, average author rating. And as you can see, it's not the data, it's just a description of what the data points might be. Publication month, it's a categorical thing. And we process text data as well, so you can tell us like, and text processing will be like BERT tokenization thing. And then it tells what the interactions are. So they say like, if they read the book, that's neutral. If they love the book, that's super positive, etc. And if you don't tell us anything about the user, then we're just gonna position them based on their interactions. And so once this is done, all you have to do is like, copy all this integration code, and then each SDK ends with learn from data, which is essentially the part where the SDK downloads instructions from our servers and then processes them and applies them on the data locally. And then once that's done, like basically the user would go and just enable an algorithm. So we have a bunch of algorithms, like recommendation one. And then like an hour later, they get their performance metric. And it's crazy because, so I said, can privacy be profitable? The craziest thing is like this data set, 720,000 users was training in like 30 minutes. If you do have, including all cycles of all processing, of like generating the embeddings, optimizing them, yada, 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 on a laptop, which is crazy compared to like how much effort it would take in a production setting differently. We're very proud of this efforts because it's now patent pending because it took a lot of work to figure it out, and then we make it available, make the recommendations available through like the same SDK. Begin and recommend. You give it the project ID and it goes. And then if you run it, you just get which books and their similarities. That's it. I mean, and the same technique, we were able to generate a lot of different things. Like we're able to do classifications. Because if you think about it, you always generate the embeddings and then you do your machine learning. If we reinvented the method of generating embeddings in an efficient way, you can do a lot with it, right? So we're able to do even analytics such as churn prediction or like identifying which customers are reducing in usage or increasing in usage in a very simple way with much simpler algorithms than you would usually have to do based on like high voluminous data. What this allowed us to do as well is to run like a lot of experimentation, because we made it available through the interface where you can say like experiment with this data set separately from this data set, and we were able to learn a lot from the experimentation process. So I guess the biggest learning for us was that I started with federated learning, which is extremely complex. So federated learning, it happened during COVID. I was stuck in my home office in Halihax, and I was thinking like, what can I do at this time? I can't go anywhere, so I just figured, let me do some research. And I was working with researchers from Oxford on this federated learning stuff, which is now used by the Facebook PyTorch. But the problem with federated learning is that we had to literally rewrite the description of every tensor to make it possible to manipulate remotely. So it was extremely complex to work with, to solve the simplest problems. And the key, like I can tell you, the key issues with federated learning. So what federated learning is that you take the model and you send it to the edge, and then you take it to another, you bring it back, so you bring back the model weights essentially, and then you send it to another device, and then you get all the model weights and you average them in a particular way. So the problem with that is you have to have balanced data on all edge devices, or otherwise you're going to have a skewed model because you've never seen the data, you don't really know what's going to happen. And the other problem with that is that if you try to apply it on simple user applications where you don't actually have voluminous data on edge devices, like for example, recommender systems, the user, yes, a single user is doing a lot of interactions, but sum them all up, they're not enough to train a model by themselves. They don't generate enough meaning. So that was the motivation to look for a different technique of process on device and train centrally. And that's pretty much it. So thank you very much.
Hi, everyone. My name is Gordon Shotwell. I'm a data scientist at a company called Scotia. We do fraud prevention. And I'm going to talk to you about Quarto and Jupyter. How many of you are Jupyter users? Yeah? Okay. So this is a website you could follow at quarto.shotwell.ca if you are interested. So a lot of my work is running a shared data science server, and Scotia has grown like crazy over the last 3 years. So it went from something like 20 users to more like 100, and it's kind of like ballpark the editors that people use on the server. So a lot of Jupyter users, some VS Code people, and some RStudio people. But what I noticed is that all of my headaches come from the Jupyter users. Every time there's a problem, every time something breaks or something can't be launched, I just go, Jupyter, just every time, Jupyter. And I started asking, like, why is this? Like, why does this editor cause me personally so many problems? Not that I use it, I'm not a Jupyter user, but other people break my server using this tool. And I think the key problem is that Jupyter uses like a fundamentally different development pattern than other computer science tools. And this causes a lot of problems when you try to integrate it with any of these other computer science tools. So a lot of the tooling around programming is built around a different paradigm than Jupyter. And the way I put this is that they differentiate between the editorial environment and the execution environment. There's like usually a clear, bright line between the times when you're editing something and the times when you're running something. But Jupyter blends those two together, and that's really part of the design of the software. It's supposed to be like an interactive notebook environment that lets you kind of like play with your data and move back and forth. But it causes a lot of problems. So some of these problems are because you're kind of like the user is also executing the data, they might do that kind of out of order, and that state can become very complex. It can become difficult to reason about or record. The code itself can cause sort of deep, profound problems to your editor. So you might like run something weird, do some sort of odd memory thing, and then suddenly like just Jupyter doesn't work for a long time, and you don't know why. It's very hard to figure it out. So it's not just like something crashing, but something kind of deeper happening to the software. And then integrations with other computer systems can be difficult. In particular, Git can be difficult. So this is the kind of JSON that a Jupyter notebook is stored. So when you just like naively try to like go check in a Jupyter notebook to Git, you try to like use any of the systems that kind of rely on Git as GitHub or something as an input, you kind of end up with this thing. And this is really easy to make mistakes with. So you can, for instance, like check credentials into your Git repository. You can check in PII that's not supposed to be in a Git repository just because it's this giant unreadable JSON blob. It's very difficult to review. So recently I came across this wonderful blog post about how the Jupyter Git problem has been solved. And the thing that I kind of was thinking about when I was looking at this is that it just shouldn't take this long, right? It shouldn't. Git as a basic sort of thing that's existed for a long time. It works with almost everything. Like it shouldn't take, like millions of dollars and 10 years of dedicated work to get the system to function on Git. So the way I'd sort of put this is that like to kind of like break it out a little bit, put a little graph on it. Most programs use this kind of like write execute model. So you have, you're writing your code, and then you have this source code, which is kind of like a rigid, it determines what the outputs are going to be, right? So this kind of like executor goes and reads this source code, parses it, and then produces some outputs. This creates a lot of wonderful things because this actually is a useful data structure. It's this thing you can sort of track over time. It's something you can analyze to do static code analysis or something like that. And this executor is kind of like always does the same thing. Like there's no humans in this part. So you kind of have confidence that once you know what's happening here, you know what's going to happen here in the outputs. But Jupyter uses what I would call like kind of like a rexecute model. You write the code, and then that kind of creates this sort of like code output construct. And then when you're kind of like running the code or working through it, that's actually modifying the sort of code output structure. And there's ways that you can sort of like parse the code out of that. There's ways you can kind of parse the code out of it. But the tool itself kind of pushes users to have this kind of like highly unsteady interactive workflow. And I think that's one of the things I've observed about people who are very, very skilled and excellent data scientists. But because they kind of maybe learned to do this as the way that they work, they kind of have a little bit of a moat around moving to sort of like more general computer science workflows. So R actually had a different whole pattern to notebook development, which is these write execute notebooks. So when you write an R Markdown notebook, this is RMD style, you actually just write the sort of code and document and text together in a single document. And just like source code, that document is a rigid artifact, right? It's just text. There's no logic in the R Markdown notebook. There's no state in the R Markdown notebook. It's just text. And what the renderer does is take that document, go find all the things that are labeled as code, pass that code through an interpreter, and then put the code and the text back together into these output formats, right? And this is a really wonderful pattern because like most of the things work right away, right? So there hasn't ever been like an R Markdown Git parser, right? Because R Markdown documents are just text, so they just work with Git, right? It's just like any other computer source code from when there were punch cards, right? It's a text that's then interpreted. Similarly, if you ever use like new make or any of those sort of like orchestration tools, they work really well with this code because that's kind of what they're expecting. They're expecting text that's then run through some kind of interpreter. Similarly, it's really, really easy to compose our Markdown notebooks with just, you could either copy and paste them together or parse them together in some other format. It's easy to package libraries, and it's also really easy to mix languages. So you can, I think, use something like 17 different computer programming languages in an R Markdown document, and they'll all play well together because it just goes and finds the Python code, runs it through a Python interpreter, goes and finds the Scala code, runs it through a Scala interpreter, right? And these are all kind of well-solved problems in computer science. But there's 3 big problems. The first problem is that it starts with the letter R, right? And so I work with a lot of Python users, and it's their least favorite letter. If you propose any kind of tool or solution, and that solution starts with R or even has an R in it, they just say no. The second sort of maybe more real problem is that it requires an R runtime, right? So R is a very niche programming language. It's not sort of necessarily installed on everybody's laptop. It's not installed on every server, so that can be difficult. And the last one is that it has a slightly inconsistent user interface. So R Markdown is a 10-year-old technology, and over time it's kind of been elaborated on to do a lot of different things. So like people write their blogs in it. I wrote my blog in R Markdown. You could write presentations in R Markdown, books, and then also just kind of data science reports. And over time, it's to accommodate all of those use cases, kind of started adding different options, and those options started drifting in terms of how consistent they were. So this is where Cordo comes in. Cordo is a new project from our studio. And the main feature of it is that it's a fully language agnostic version of R Markdown. So it's a TypeScript command line utility. It doesn't have any R or Python dependency. You can use it for just R. You can use it for R and Python or Observable or JavaScript or Julia. It also has a lot better branding, just because, speaking personally, I've had at work many times where I've just seen people waste like huge amounts of money on things that really could have been a scheduled R Markdown document, right? And I have not been able to convince a single one of them to use a scheduled R Markdown document to solve their problem. But every one of them, as soon as I talk about Cordo, they're really excited about Cordo because the capabilities that it has and how simple it is are really powerful, but it doesn't start with the letter R, so it kind of like gets through the gate. And then lastly, it's got a unified extensible interface. So it's kind of, the interface is focused a little bit more on Pandoc, which I'll get to in a second. And so that means that it kind of like, it's a lot more consistent and easier to work with. So how does this work? So you write a QMD document, which looks a lot like an RMD document if you're familiar with that. So it's Markdown with sort of specific code chunks. And then when you render that document, Cordo goes and passes the code through an executor or through an interpreter, and then puts together this Markdown document, which is so the output of the code is turned into Markdown, and then text is put where the text goes, just as Markdown. And this goes to a system called Pandoc, and Pandoc is this really incredible tool for turning documents into other documents. So it has basically what's called an abstract syntax tree on top of documents. So it says for a PDF, this part of a PDF kind of maps on to this abstract syntax tree, which then maps down to a Word document or a PowerPoint document or something like that. So with Pandoc, you can take this Markdown file and render it into lots and lots of different formats. So this slideshow is done that way. You can do HTML, of course, websites, books, all these types of different things. This is what the code format looks like if you're totally unfamiliar with it. So so this is just something you can write in a text editor. And basically the sort of two things. So most of this is Markdown notation. So those are like headings. And then you have these little backticks that define like inline code. So this would be like an inline code chunk. And then you could have code chunks that sort of specify the language here. And then you can just run code. So what Cordo does is it goes and it finds anything like this, passes it through the interpreter that's labeled by this thing, and then produces the output. So in this case, that would produce an output that looks like this, right? Does the calculation of the two, puts out the text, just like that. So the main sort of advantages of this is that it moves you from this kind of like fuzzy place where you're not really sure what your source code is. Like, how is it the sort of document you've produced, or is it the one where you produced and then ran some chunks? Instead, you have this sort of clear idea of like the QMD file that you're working with, that's the source code, right? So that's the thing that you can check into Git, you can share with people, you can test more easily, you can analyze more easily. It gives you all the benefits of Pandoc, so you can render really beautiful sort of full-featured PDFs. There's lots of different academic journal formats, things like that. Great caching, and you can compose notebooks together. So you can have lots of notebooks together that make a website. If you want to look at a website like that, you can look at my website. But you don't actually need to abandon Jupyter to start using this. So you can still use Jupyter as your main editorial environment because Cordo can render Jupyter notebooks without authentication and preview them, and then you can also convert really easily back and forth between a Jupyter format and a Cordo format. So you kind of don't need to actually change much about your work. And then one thing that I would recommend is this NBDev, which is by the Jeremy Coward, who does Fast AI. He kind of uses Cordo as basically the publication layer on top of that kind of notebook development pattern. So the way to get started, you can go to cordo.org. It's also included with the latest release of RStudio, so just you don't need to install anything. The RStudio visual editor is really wonderful, whether or not you're an R user. It's a really great visual markdown editor, which kind of lets you sort of use these things really well. There's a VS Code extension that's also really good. And so the main sort of rules here is that what you should try to do is store the code asset as a QMD document. So that's something where it's if you're working with Jupyter notebooks, great, work with it. And then you want to at some point write and check in this text file that's just the document in the report. And when you share it, you should share it with that thing and then probably some kind of environment definition, if you use Conda or virtual env or something like that. And the thing that you share with people who want to read the code, who aren't going to go execute and work on the code, but just want to read the report, is the render document, which can include both the code that you use to do it, as well as the sort of prettily formatted output. And that's what I've got. So you can contact me at my website or tweet me at Shotwell.